Наш последний доклад сегодня, наш вообще последний доклад на конференции. Будет еще заключительное слово, но это не доклад. Наш последний доклад опять про криптографию, и на этот раз про другой аспект. Мы будем обсуждать, как патчить OpenSSL, и как вообще, как разработчикам, Secure Software Engineer, я думаю, обычные разработчики с этим не справятся, да? Как разработчикам подменить реализации криптопримитивов в библиотеке, которые они уже используют, если у них нет доступа к коду. Да, то есть если у вас уже рабочая система, если у вас уже там есть какая-то криптобиблиотека, например, OpenSSL, и если вы поняли, что нужно что-то поменять, как это можно сделать на лету, не имея доступа к коду? Об этом нам расскажет Игнат, Security Software Engineer, компании Cloudflare, который уже не один раз занимался патчингом OpenSSL. Как это, карьерный рост.
Да.
Давайте поприветствуем Игната.
Спасибо. Как объявили, презентация будет на английском языке. Официальная версия, потому что у нас много иностранцев, и надо, чтобы они тоже хотели послушать, и было интересно. Неофициальная версия. И, кстати, вам это намного выгоднее. Английский намного компактнее язык, поэтому просто так будет быстрее, и все пойдем гулять, ладно? Если кому непонятно, что я говорю, словите меня, купите мне пиво, и я вам переведу отдельно.
Или вот возьмите headset, потому что у нас потрясающий перевод.
Или так. Но лучше купите мне пиво. So today we are going to talk about live patching with crypto with OpenSSL engines. So, who here doesn't know Cloudflare? Who here have a website and doesn't know what Cloudflare is? Okay, good. Otherwise, you're missing out. I worked at Cloudflare at Performance and Security. I like low-level stuff. I'm dealing with OpenSSL, crypto, bootloaders, Linux kernel, and many other things. And today I'm going to tell you about how to patch weak crypto in your OpenSSL-based proprietary tools. Why focus on OpenSSL? Because actually OpenSSL is very widely used. Like some statistics say that 80% of the software crypto tools are using OpenSSL. So although we're limiting ourselves to a single crypto library, we're actually covering a wide spectrum of software. Okay, so what does it mean, weak crypto? Like, what is the difference between weak and strong crypto? And because this is a final talk, I will not bore you with formulas and math. I'll just have this simple picture which displays weak crypto. So this is your house. It looks like it's secure. It does the fact. But if your attacker has sufficient resources, they can just blow away your security in like that. Versus like strong crypto is a brick house, right? So no matter how hard the attacker tries, over time you're still secure and they just can't break it. So this is like okay, so there is weak crypto is bad, strong crypto is good. Like, why do people use weak crypto in the first place? And there are a couple of reasons. Like, some of them are like developers do not know what to use. Not all of us are crypto engineers or crypto experts. And when you go to OpenSSL, you see a wide range of choice of algorithms you can pick from, and you just don't know what to pick. And if you do pick an algorithm, there is also like these additional parameters like initialization vectors. We just seen that they have to be unique. There are requirements to them. So people just do not know what to do. Like, some people select ECB mode just because it doesn't require any initialization vector, because they don't know what to put there, right? There is also these government regulations, this infamous US export cryptography, where previously in the 90s, United States allowed exporting cryptography with very weak keys, not more than 40-bit entropy, which is basically no crypto. It's weak crypto, it can be blown away. And you can't do anything about it. And finally, strong crypto actually becomes weak over time. So first of all, here's some advice if you don't know what to use. We've been repeating here over and over, never roll your own crypto. And not only don't invent your own algorithm, if you even pick the algorithm, like available algorithm, but not know exactly how to generate a proper IV or something like that, don't guess, just ask people for help. Don't copy-paste from other projects on the internet, from Stack Overflow. This is basically because they didn't know what to use as well, so their choice may be wrong. They might have a different use case, and in their implementation, this choice is good and the system is secure, but in your case, it will be insecure, right? And finally, don't try to use low-level primitives. If you really don't know what to use, you better not use like low-level crypto libraries, but pick a high-level crypto libraries which provides you some use case-based primitives. For example, if you need file encryption, pick a library which says, here is a function to securely encrypt a file. And underneath, this function will make proper security choices for you. So some of the examples is Themis from Kozak Labs, which I helped to actually bootstrap, Lipsorium, or Google Think. So why strong crypto becomes weak over time? There are basically two reasons. First one is just the research is ongoing, and people come up with new algorithms how to break crypto. So these algorithms were secure in the past, but now new techniques were developed which help the attackers to more efficiently crack the algorithm. This is basic science. And second is just pure rapid technological advancement. So computing power becomes cheap, resources become cheap. Now we have the technology to combine many small computers into big clusters, and we have access to tremendous resource which we can reuse to crack algorithms. Also there is and this is evolutional, there is also the revolutional part, something like quantum computers. If somebody builds a quantum computer, elliptic curve cryptography, which is today is considered the state of the art of cryptography, will be completely broken. So crypto even strong crypto at some point will become weak, and then you need to do crypto maintenance. You need to replace it, right? So what do you do? But replacing crypto is not that easy, right? So if you develop your own product, if you have your own software, you kind of change the algorithms, get some advice, and replace the weak crypto with strong crypto. But many of us are using services, proprietary tools, vendors, and external sources, and you don't always have the opportunity to just go and swap algorithms. And then you go to your vendor, but vendor is either slow, they will say, yeah, we'll update it in the next release cycle, and it will be in a year, or they don't want to do it. You also have the problem of abandoned software. You have the problem of software which has no source code available, the source code was lost, and there are also additional costs. Vendor must say, yeah, we'll do it, but we consider it a feature request, so pay us additional $2 million to do that. It's not always great, right? So let's imagine we're in such a scenario, right? So we have a proprietary system based on OpenSSL, which uses with crypto, and we want to replace it, right? So what is the system? Let's imagine it's some kind of proprietary storage solution. It's either a relational database or an object storage, but it doesn't matter in this case. The key point is that it indexes its data or object it stores via hash function. So it creates an index of an object via hash function and uses OpenSSL as a crypto backend to actually take this hash function implementation. So you're good, you bought this software for a great amount of money, and you use it for 2 years, and later, at some point later, you invite a so-called external audit, which is the guys who presented on the stage yesterday, right? And they you ask, what's happened? They say, you're using SHA-1. I say, yeah, so what? And didn't you hear about this? Everyone know that? This is even an old stuff. There is new stuff coming up now. And the TLDR of this is we have broken SHA-1 in practice. You go to this website and you will see the first line. And yeah, And the auditors say if you don't fix it in 2 weeks, you will lose your compliance, right? You go to your vendor and they, please replace SHA-1, but the vendor will usually say like, yeah, this is fine. If you read the paper, they say the SHA-1 broken in these cases, but in these cases it is still secure. We believe that we're not vulnerable, or we will need like 2 years to do it, right? And you somehow have to deal with that. So, yeah, you said, okay, we'll do it ourselves, right? So to understand how to patch proprietary software, you have to understand how shared libraries work. Because most likely, hopefully, they will use shared libraries. So imagine you have 2 processes. You have like a privacy client, and you have a database. So by the way, any resemblance to real software is coincidental. So yeah, and they both require some cryptographic services. They need cryptography. And what a shared library does, it provides these services. So you have a library, it says, yeah, I have this cryptography, and software uses it. It's cool. What makes it shared is that the shared libraries are libraries which are not part of the main application. They are more like a separate package, and they are dynamically linked in runtime. The code is shared between programs. That's why they're called shared libraries. The nice part about shared libraries is the code is loaded only once in the memory. So if you have like 10,000 processes which need OpenSSL, you have only one copy of OpenSSL. And because it's not part of the main application, you can update them independently. So you can update your OpenSSL, and all the application requiring it will magically use the updated version, which is cool. So I know I told you that the software is proprietary, but let's imagine we're sneak peeking on the vendor side and we kind of see the source code, so you have the basic understanding what's going on. And this is our stripped down proprietary database. I will only implementing the hash part here, the index calculation. And this is basically a command line tool which calculates the hash of a file. Simple as that. And this is a main function. We will have several iterations of the tool, but all of them will have the same main function, so I'm showing them only once. And so the main function just takes a file as a C-level file object and passes to a function called hash. And then the different implementation calculate the hash. So the first iteration of the tool you received looks like this. If you're not very good at digesting C code, I will quickly go through what's happening. So first of all, what you have here is you have a fixed buffer. You read all the file into the buffer, and then you call OpenSSL with SHA-1, calculate the hash of the buffer, and then print the result. Easy, right? Let's check if it works. By the way, this is supposed to be a demo, and I really promise you this was copied from a real terminal, but like the visibility is much better, so pretend it's a real demo, right? So yeah, let's try let's hash ABC using our custom tool. We see some hash. We may suspect it's SHA-1 because we were told by auditors, so let's check it. Cross-check it with a well-known implementation, right? So you can also hash ABC in the SHA-1 sum tool, and you will see the same output, right? And using the LDD command, you can also check which libraries this tool needs. So if you run LDD custom hash, you will see that this tool requires OpenSSL, which is called libcrypto in Linux usually. Okay, so how to understand the swappy part, we need to understand the lazy binding on the shared libraries. So let's say you have a process. You start the process. How does the process find functionality in the shared library? So the first thing the process does is process talk to a special piece of software on your operating system which is called dynamic loader. It doesn't actually talk. It's actually the dynamic loader reads the image of the executable and finds out which libraries does it need. Then the dynamic loader will load all the libraries needed for the process. And that's it. Nothing happens. And the process starts executing. So no function resolving happens at this stage. later, that's why it's called lazy binding. When the process needs to calculate the hash, it needs the SHA-1, it talks to dynamic loader again, saying, hey, I need the SHA-1. Where is my SHA-1? And so the dynamic loader says, hey, who of your libraries has SHA-1 here? And most likely one of the libraries will say, yeah, I have SHA-1, and then the process can use SHA-1. So, and in this case, usually if you compile your program normally, for each function, you will have at most one library which is implementing it. So although the dynamic loader asks who has, usually only one library will respond, right? But you can change that. And the way how you do it, you can use this magic environment variable called LD preload. Who doesn't know what LD preload does? Okay, there are people, so I'll describe it, yeah? So LD preload tells your dynamic loader or linker to load additional libraries into the process space, which were not even required by the process, right? And why it's called preload, these libraries are loaded before even all the main code is loaded in the memory. So it's the first thing your program gets. And they're mostly useful to override, modify, hook, or tap exported functions from shared libraries. If you want to read more, here is the link on the Linux man pages, on the dynamic loader man page, actually. So when you define LD preload, you change a picture slightly. So the program didn't even start, but the dynamic loader already loaded your custom library. Then the usual thing happens. It checks which libraries does the application needs, loads these libraries. Then at some point, when the program needs the SHA-1 implementation, it goes to dynamic loader, asks, hey, who has SHA-1 implementation? The dynamic loader queries all the libraries. But now two libraries respond, we have SHA-1, if you implement another SHA-1 in your library, right? And the magic of the loader will go, it will divert the program to the first library which was loaded. And because we used LD preload, our library was loaded first, right? So the program will then go to our library for SHA-1 and not to the standard OpenSSL one. So now we just need to figure out, we have a way to hook functions on OpenSSL. Now we need to figure out what to hook, right? And we can do some symbol analysis on the executable, and we can see that it requires two functions from OpenSSL. Then you go to read the descriptions of the function, and then you try to understand how to hook it. And eventually you will come up something like that. So you will write your own library with the function with the same name as the OpenSSL function, but you will override the code. The typical approach for hooking the function is you don't want to override the function completely. At some point, you want to do just some pre-processing and post-processing. And at some point, you want to call to the real function. So the first thing you do, you find the address of the real OpenSSL function so you can use it later, right? Then you do your magic, you do a pre-processing magic. And in this case, what we do is if the caller calls us and asks us to calculate a SHA-1 hash, we actually call back the real OpenSSL implementation, but replace the identifier from SHA-1 to SHA-256. We also add some debugging output, in this case, just to ensure our code runs, so we can see it. And finally, what we need to do, we need to remember that SHA-1 is shorter than SHA-256. So SHA-1 is 20 bytes, SHA-256 is 32 bytes. So we can't just return to the caller 32 bytes because they might not have a buffer large enough to hold 32 bytes. So we just cut the buffer to 20 bytes, right? So let's see how it works. We compile this code into a shared library of our own. And we start the process specifying the LD preload environment variable and point it to our library. Now we see our debug output, and we see a slightly different hash. We can cross-check it with the real SHA-256 implementation, and we will see they match. So we now successfully replaced SHA-1 with SHA-256, although we cut it. Good. So what we did here eventually, we had this picture, so we had our custom tool. It used a function from OpenSSL. We just cut off this connection and divert it to our custom library, which does two things. It replaces the identifier to SHA-256, so it tells OpenSSL calculate SHA-256 instead of SHA-1, and then cuts the result back to 20 bytes, not to confuse the calling application. If you were attentive enough, you'll notice that the previous vendor tool had a flaw. It had a fixed buffer on a stack, which was only 4 kilobytes. So it means that the tool cannot calculate the hash of files more than 2 kilobytes, right? Because it reads the whole file in the buffer and calculates the hash of the buffer. And this is a bug. And you might reported it to the vendor, you might find it out, and they fix it, right? They modify the code to calculate hashes of files of arbitrary size. But they need to change their program. So instead of calculating a hash in one call from a buffer, they switch the implementation to use a so-called hash interactive mode. So they basically create a hash object. They read the file by chunks and feed these chunks into this, iteratively into this hash object. And then finally they get the result and print it, right? But now when we ask the vendor to fix the bug, they fix the bug, they provided the update, our fix does not work anymore. So we don't see the debug output. And if you're good at remembering numbers, you will remember that this is a SHA-1 hash of ABC, not SHA-256, right? So what happened here is we no longer intercept the function calls. And because they changed the implementation, although they didn't change the interface, and now they're using different functions. We're hooking one functions, but they use different functions from OpenSSL. So we need to fix our fix, right? So instead of our fix, we now need to hook two functions. Again, as before, we resolve the addresses of the real OpenSSL functions. Then, secondly, in the first function, we'll replace the identifier from SHA-1 to SHA-256. And in the final function, we provide our own buffer and cut the result to 20 bytes to return to the caller. Add our debug output. Yeah, and return to the caller our cut down hash. So let's try if it works now. Yeah, we see the debug output. We see the SHA-256. So we're good again, right? But the vendor, again, doesn't update. So they hired a new engineer, which says, nobody calls in OpenSSL like hash functions directly. They have these nice abstractions called BIO, which stands for basic input output, which abstracts anything to a stream, and you can stack streams on top, so you can have much nicer implementation. You can abstract a file as a stream, you abstract hash as a stream, then you so you could create two streams. One is file stream, one is hash stream. Then you stack them together. Then you just read from the stream, and in the same function call, you're reading a file and calculating the hash at the same time. It looks much nicer. Let's use this. Yeah, and we just return the result to the call. When they deliver the update, of course, our fix doesn't work anymore because, again, they modified the functions, right? If we analyze now, they're using a complete different set of functions which we never hook. So we need to fix it again. So we create another fix for our fix. We hook different functions names, but we basically, the approach is the same. You find the real functions, you replace the ID, you print our debug output, and you return the stripped down result to the caller, right? So let's check if it works. Again, yeah, it works now. Good. But this is just like a wacky race, right? Like each time the vendor does an update, we have to update our fix. So is there a better way? And in general, no, but we can focus that we're using OpenSSL. And can we do something OpenSSL specific, but still cover like 80% of world crypto usage, right? And the answer is it's called OpenSSL Engine. So it's a less known feature of OpenSSL that OpenSSL has a as a kind of an extension framework. You can write extension modules for OpenSSL. And you can use this to add new crypto algorithms into OpenSSL or replace existing cryptographic algorithm implementations. So for example, if you don't like their implementation of SHA-1 or SHA-256 and you can come up with a much faster one, you can just replace it dynamically and it will work. And this is mostly useful to pair OpenSSL with some kind of hardware-based crypto devices like crypto keys or HSMs. They usually provide their own engines, so you stick it into OpenSSL, and any OpenSSL-based product now can use the crypto device. If you want to read more, here is a link, which is an intro how to write a simple engine. So let's write our own OpenSSL engine, and we will replace the SHA-1 implementation, but we will replace it with SHA-256 implementation. We pretend we're SHA-1, but we will be calculating SHA-256 under the hood. So for hash engines, you need to implement 3 functions, like 3 callbacks. It's like init, update, and final. And basically what you do is in each function, you pass the callback to the corresponding OpenSSL function, but instead of SHA-1, you pass it to SHA-256 variant. And let's not forget, in the final function, we will produce our debug output just for ourselves, and also